we could start. But before we start, let me briefly introduce our speaker, Professor Reinhard Folk. His research interests lie in condensed matter physics, phase transition, as well as the history of physics. Moreover, Professor Folk participates in many projects aimed to strengthen cooperation between the countries of Central and Eastern Europe. And during his career, he was awarded the Walter Schottky Prize of the German Physical Society, as well as Doctor Honoris Causa by our Institute for Condensed Matter Physics. So let us welcome Professor of the Institute for Theoretical Physics, Johannes Kepler, University Linz, and our big friend, Professor Reinhard Folk.
Thank you very much for the introduction. And my talk today is about the thesis of Ernst Ising. It's 100 years ago he started this thesis. It was in the autumn of 1922 when he got the theme by Wilhelm Lenz. And one of the reasons, I think, was that just at that time, in the autumn of 1922, there were three persons which were important for this thesis at the University of Hamburg. It was Wilhelm Lenz, of course, and Walter Schottky. And I will explain this in the later when I went on with the talk. However, I want first show you Ernst Ising's birthplace, because it is in some way related also to my curriculum. So you see, do you see the cursor? So you see the birthplace. He was born on 10th of May in 1900. And if you follow the tram, you see a big house with 6 windows in a row. This is high-marked 64 and 62. This is the birthplace of Ernst Ising. You also see a monument. It's Wilhelm III. He was King of Prussia during the Napoleon Wars. Now, this place has a long history. 2 years after he was born, the family moved to Bochum. So he left Cologne. But the place is important for the history of the Ising model even later. In the years 1933, Onsager met his wife in Cologne. He was a visitor of Falkenburg, and he moved to visit him to Cologne, and he saw the woman. It was a relative of the wife of Falkenburg. She was an Austrian lady, and soon they married. This was important because Onsager moved back to America. World War II began, and because he was married, he was from Norwegian, and because he was not an American, and because his wife was an Austrian, which was so he could not take part on the projects during the war, and he had a lot of time, and so he could solve the Ising problem. So in the 30s, the Ising had already finished his thesis. He left the University of Hamburg. He went to Berlin, and he became a teacher. And due to the Nazi laws in 1933, he was dismissed. And so he had to go to a Jewish school at Kapput near Berlin, where he could teach Jewish children. So the Nazi time was a very severe time for Ising. My parents moved for the first time to Cologne in the year 1936. But they were lucky because they could leave the time before the war ended in 1945. And you see the place where Ising was born. You see here the place, Heumarkt. You see here the rest of the monument. It was completely destroyed. And even people, it was not clear if Cologne would ever be recreated. But because you see the cathedral of Cologne, because the cathedral was intact, it was decided by the people to recreate Cologne. And there was also the Marshall Plan, and there was the economical miracle in Germany. And so the city could be recreated. And I was born in 1945. My parents were back to Austria. And in 1953, 8 years later, they moved the second time to Cologne. And I went to elementary school there. And of course, we were half an hour from the center of the city. So I was at these places, and I know all the surroundings, but I didn't know nothing about Ernst Ising. I learned about the birthplace of Ernst Ising by Sigismund Kobe's webpage, where I found the address. Now, the place was completely destroyed and had to be recreated. And you see here how it looks today, so to say. I left after 1.5 years Cologne with my parents, but I returned about 25 years later when I was visitor at the scientific center in Jülich. So I was often in Cologne, and I was often in this place because, as you see, this was a place where you have a lot of breweries, and people came together drinking beer. Ising, after he was dismissed, was in the year 1945 already in Luxembourg, and he was freed by the Allied army. And in the year 1953, when I was in Cologne, he was already in America, and he got his position at the University of Bradley in Peoria. So everything went to a lucky end, but you see what can happen to scientific landmarks over the time. But now let me go to the thesis of Ernst Ising. There are many papers about Ising's thesis, but he created so to say, made an impact to the field of phase transitions, and it treated a very important problem, which also appears, for instance, in the Quran, because it made a contribution, as you see here, to the theory of ferro and paramagnetism. And in Quran, you find a surah where it is written, and we sent down iron in which there lies great force and which has many used for mankind. So this is an, so to say, almost scientific remark. It is, in fact, the first remark in a religious text which tells us that the iron comes from the stars. So iron is not, the Earth contains iron, which was in the process of the development of the stars and then accumulated on Earth. So this is a very interesting first remark of this astronomical feature of iron. And the problem at that time, when Ising began his thesis, was to have an explanation for the phase transition to the magnetic state in ferromagnetic materials. There was already 5 years about after 1900, the so-called mean field theory, or the Curie-Weiss theory, developed. It was a theory which assumed that in a solid, in a magnetic solid, which consisted of elementary magnets, those elementary magnets are in some way correlated and create a magnetic internal field. It was quite similar to the theory of van der Waals, who considered the phase transition between gases and fluid state and gaseous state and fluid state, from gas to liquids, and he assumed an inner pressure which produces the denser liquid, the phase transition to denser liquid. And the same should be done by the inner magnetic field in ferromagnets. If you take a ferromagnet and cool it down, it might cross the so-called Curie temperature and goes over into a magnetic state. So this Curie explanation of the Curie temperature was a great problem, and the Curie-Weiss theory thought it could explain it by the inner magnetic field. And the inner magnetic field should come about by magnetic forces. So they looked for magnetic materials and studied this phase transition. And one of these ferromagnetic material was Pyrrhotite. It consists of iron and sulfur. And I show you here how it looks like. It's found on Earth in this state, solid state. And here you have from Humboldt University the structure. You have the iron as the red, in red, and sulfur in yellow or white spheres. Now, this material has a special property which was also very strange. It is not in every direction ferromagnetic. It's only in a plane ferromagnetic. So the inner field has a certain direction. And Pierre Weiss, already in 1905, made experiments. He looked at the magnetic field perpendicular to the magnetic plane, and then changed the external magnetic field. So, depending on the direction of the external magnetic field, you get different magnetic fields and different magnetic intensity within this plane, depending on the how the field, the external field, is directed in the plane to the planes defined by the structure of the solid of Pyrrhotite. This experiment led Wilhelm Lenz, 1922, to suggest a different and new theoretical approach to ferromagnetism. He said, well, it seems to be important to look at the direction the elementary magnets in a ferromagnetic material can be taken. So if you have in quantum mechanics, already at that time, it was clear that the direction in space of the angular momentum had to be quantized. So it's not every direction is allowed. And the mean field theory and the Langevin theory assumed that the magnetic moments in the solids can direct it in every direction and rotate about every angle. So Lenz assumed that there is no free rotatability within the solid. There are certain directions which the elementary magnets can take. And the simplest model you can suggest is that they can be parallel, so you have one direction and you have the reverse direction. They could be, so the elementary magnets could be parallel or they could be anti-parallel. And another assumption he made was that this flip of the direction of the elementary magnets is induced by electrostatic forces. Because the magnetic forces, if you take the interaction of magnetic dipoles, you see it's too weak. It would not give the temperature which you observe at the phase transition in the ferromagnets, the Curie temperature. The Curie temperature is about 1,000 degrees, and the temperature, if you take into account only the magnetic interaction, would be only 1 degree. So it is much too weak. That was a problem. Although the mean field theory was a very practical theory to treat ferromagnetic materials, it was a problem that it could not explain these temperatures, and of course there were other deviations of the theoretical predictions of mean field theory. In 1922, as I already mentioned, Walter Schottky came to the University of Hamburg, and it was in September 1922, and he already had presented a paper about the rotability of the magnetic axis in solids, which could explain the Curie temperatures. What did he do? He looked at the elementary magnets in the solids. And what is an elementary magnet? At that time, it was a magnetic field could only created by ampere currents. So if you have an atom and you have a circling electron, the circling electron is a current, and you have a small magnetic moment. And if you have two electrons, you have two magnetic moments, and the two electrons can interact by the magnetic moments, but they also can interact by Coulomb forces. And the Coulomb force depends on the distance of the two electrons which you have brought together in the solid state. Now, if they circle in the same direction, you can fix the distance by a phase relation between the two electrons. Now, for instance, if you fix them rotating at the same phase, so to say, you have a smaller distance than if they rotate with a phase relation of pi. So if one electron is here, the other is here, the distance is different. And you can calculate the Coulomb energy of the two states. And you see that with a phase relation, you can look for the state which has the smallest energy. And then you flip one magnetic elementary magnet, so you circle around not in the same direction, but in the reverse direction. And then you see you cannot keep the long distance, but you get shorter distance, though you need electrostatic energy to flip the spin. And that you could do either for electrons above each other, circling, or beside each other. And Schottky developed this theory with what I told you, a phase relation, a synchronization of the electrons, and he called it rotoactivity. And the main point was that he could invoke Coulomb energy, and the result was that if the two elementary magnets are parallel, their Coulomb energy is less than if they are antiparallel. And the energy difference was of the size of the Curie temperature. The interesting thing is that in his paper, which was published 1922, he also found it could be that the parallel, depending on the phase relation, the parallel position could be with less energy. So in fact, he already also found the antiferromagnet state, but it needed more time to find it by Neal later, but he called this neutral magnetic phase when these energy relations hold. Now let me go to Ising's thesis. So I think Lenz decided, Ising was the second student for a thesis with Lenz, and I think Lenz decided after the paper of Schottky that he has now a theoretical microscopic idea and theory which could explain ferromagnetism. But in order to explain the ferromagnetic state, he should have to calculate the macroscopic properties of the solid. And this is done with statistical physics. So a model had to be set up, and that was the task for Ising. So Ising started with the simplest model he could make, and that was the chain. He has a chain of elementary magnets, and they could be in different configuration, either parallel or in this direction or in the other direction, or they could be antiparallel. And he assumed he has a magnetic field in the direction of the chain, so as it is shown here. Then he has, if he has this, he has to look at the energies of each of the configurations possible. And he said, well, if they are parallel, let's take the energy 0. If they are antiparallel, I need some energy. He called these energy places. And in order now to calculate the macroscopic quantities, he had to calculate the partition function. And the partition function is a sum over all the configurations. And here is the number of different configurations with spin up, down, and the number of the energy places. And then he had to give them the Boltzmann weight to calculate the energy of the system in an external magnetic field here and at a certain temperature. So here you find the spins, the elementary magnets in direction of the external field, against the direction of the external field, and the energy places. And this is the Coulomb energy which Schottky had a model for. You can, these calculations you find in his German thesis, in Ising's thesis, but it appeared already 1939 in the textbook of the American physicist Francis Bitter, and who I come to the derivation of the results immediately, but he also had 1934 discussion, an elementary discussion of ferromagnetism, where he cited Ising and where he looked at the different results you can obtain from such expression. Because you also can derive with this expression mean field theory by assuming a certain expression for the number of configurations and a certain number of energy states. I will come to this point immediately. So when Ising began his thesis, he had the following simple model. He had configurations up and down, and he had energy places in where the two elementary magnets are not parallel. The number of up elementary magnets is nu1, the number of down nu2, and the number of energy states sigma. And then the Boltzmann weight is given by this internal energy, and this is the weight in the external field. You find the expressions here. Here you have the external field. Since he was interested in the magnetism, he always started to calculate the magnetization or magnetic intensity, as they called it at that time. He could solve this model, and he got this expression for the magnetization for the chain. And if you look at that, if you set the external magnetic field to 0, also the magnetization is 0 for every finite temperature, which appears in this alpha and beta. So he came to the result, no magnetization. So he thought, what he was really interested was, well, we have a three-dimensional solid. Could we get magnetization if we go to higher dimensions? So let us go to a plane. And how he constructed the plane. In the thesis, he said, at the end of this section, we should mention an idealized case of a plane model. The elements are arranged on the plane in n parallel chains. These are the n parallel chains. And each chain contains n1 elements. As previous, each element can assume the two positions in which the magnetic dipole moment falls in the direction of its changing. But now the elements within the change are not supposed to act on one another, but on the other hand, it requires an energy EI, internal energy, when two ejectant elements of one are folded over the two ejectant chains. So he said, well, in this change, there is no interaction. This is not an energy place. But you have an energy place here in this change where the elements are perpendicular to the chain direction. So, in fact, he assumed again only one chain independent of a second chain and so on. So, first, he used the same energy for the chain where the field is in this direction and for the other case. So in fact, Schottky's model was anisotropic. It was, you have a different energy if the electrons rotate above each other, and in this case, if they rotate beside each other. But this is only a slightly difference to Schottky's model. But the main drawback is that he didn't take into account the interaction of the different chains. And therefore, he thought, well, if all the chains would be in the same direction, there would be a larger magnetization, but you get only, a factor n1 here, because you have the chains with n parallel chains, and all the chains are parallel, you have n1, but the expression remains the same. And if you put the external magnetic field 0, you have also the magnetization 0. Now let us go to the three-dimensional model. In the three-dimensional model, he not only have the situation that he has the planes and several planes above each other. So he has to take into account that he has an anisotropic model, and therefore he has energy places if the spins are in this, the spins were not alive. The elementary magnets are in that direction, or if they are in that direction. So he had different energies according to the anisotropic model of Schottky. And he said, we imagine that the three-dimensional ferromagnetic crystal constructed of n1 regularly arranged chains, as we considered above, again, each can interact, take two positions. However, the portions of the moment perpendicularly require too much energy to be realized. This supposition can only be favorable for the intensity of magnetization in the direction along the chains considered by us. We determine again that the energy disappears when all elements are similarly orientated. So he took, instead of different planes, he oriented the elements in all planes in the same direction. And by this simplification, he already reduced the three-dimensional model to a one-dimensional model of different planes. And in the thesis, he didn't work out this spatial model. He only noted in the thesis, at the end, it is conceivable that the spatial model in which all neighboring elements somehow act on each other has a necessary stability in order to prevent the magnetization intensity with the external field from vanishing. But in the publication, he said, also one does not arrive at a different result using a three-dimensional model, which agrees with the assumptions above. Well, again, these planes, we can show without difficulty the result in an idealized border case, when all the planes are oriented in the same way. And in the idealized border case, the energy should be so large that two neighboring elements lying next to each other or are never oppositely oriented, and however that only a tilt over of the elements in layers occurs. And then he gets a result where this n1 of the layers appears at different places, but the result has the same structure. And if the external field alpha is 0, again the magnetization is 0. Now I want to show you how he calculated his model of the chain, because he calculated all the cases he considered later in the same way. What do you have to do? I already said, you have to calculate the partition function, and it contains the configurations, the number of the elementary magnets, the external field, and the temperature and the energy. So you have to sum up of the overall configurations, and you have to sum up over all energy places, now called S. And he has to consider, if he looks at a finite chain, how the boundary condition looks like, so to say, how the last elementary particle magnet is up or down. And then he has to sum up to get the partition function. But the partition function contains a problem. It's a problem that nu1, the up magnets and the down magnets, have to be the number n of all the elementary magnets. So it's a condition which you have to take into account if you perform the summation. So he had to find a trick to overcome this condition, this internal condition in summing up. And in order to do so, he said, well, let us not calculate the partition function for a chain of length n, but let us sum up all chains of length n, but multiply each partition function by the power x of n, and sum over all n to get an auxiliary function. Now he has an auxiliary function. And he said, if I have the auxiliary function, I can expand the auxiliary function in x. And what do I get? I get the partition function of n. Now he could do this summing up without this auxiliary condition, but because the binomial factors which he had already worked it out properly, and he get a ratio of two polynomials, a polynomial in the numerator and in the denominator. And well, that is a polynomial of some degree, and you can write this polynomial as a product of these two linear expressions. Well, just you look for the zeros of the polynomial, and then you have it in the denominator, and then you can make a partial fraction expansion. And after the fractional expansion, you can an expansion in x. And what you get is f of x, this function, as a sum of powers in x, and then the expression for the partition function. And the miracle, I think, which happened here was that the mathematics of Ising overtook the status of the physical theory, because what you get here, you see it in the next transparency. You get the partition function as a power in the zeros of these polynomials. And the polynomial is just the polynomial which you calculate when you calculate the eigenvalues of the transfer matrix in the later found spin model, which is equivalent to Ising's elementary magnetic model. So in the success in the physical theory led to the they found the spin, and that the spin is the reason its magnetic moment, the rotating electron itself, its spin has a magnetic moment, and this magnetic moment creates the phase transition, and you have to calculate the quantum mechanic energy that can be done with the theory of the new quantum mechanics, which was developed after Ising had finished his thesis. Heisenberg and Schrödinger developed the new quantum mechanics. I cannot go into details. And Heisenberg found the explanation for the interaction of the electrons, which is the Heisenberg exchange interaction. And many things were the input into this theory. Instead of synchronization and phase relation, you had the Pauli principles, you had the knowledge that the electron is a fermion, it's a spin half particle, and the wave function of the electron should be anisotropic. And in this way, you can explain that a certain the Coulomb interaction governs the size of the Curie temperature. And Pauli in 1930 wrote down with his spin the model for the mathematical expression for the Ising model. You know from your lectures, it's the usual spin model, and often it's called the Ising model, but Ising didn't have any knowledge about the spin. So these are the two eigenvalues of the chain in the Ising model, and it's equivalent, or it's the same as the eigenvalues of the corresponding transfer matrix of the Ising model in the modern formulation. And the factors you can here also calculate, and then you can make Ising made in his thesis now a figure for the magnetization, the magnetic intensity, as function of alpha. It's a combination of magnetic external field and temperature, and you get the well-known figures here. If you make a modern calculation, you easily can calculate other quantities, thermodynamic quantities, let's say the specific heat, the magnetization, or the susceptibility. This have been taken from the internet, and it was calculated by Alessandro Cotello in 2015. Now there is another relation, apart from the idea that the Coulomb energy governs the interaction between the elementary magnets. It's much easier to calculate these things if you have no magnetic external field, and you know that the Onsager solution for the two-dimensional Ising model is the solution without external field. And then you can calculate quantities like the specific heat. Here you have the Hamiltonian for the Ising model, how the partition function looks like, and it's easily calculated, and here you have the expression. And if you now calculate from the partition function by taking the derivations for temperature, you can calculate the internal energy, and you can calculate its specific heat. And what you have here is the specific heat of a model consisting of independent, non-interacting spins, which can only up and down. It's a two-value model. And this specific heat shows at low temperature what is called nowadays Schottky anomaly. And this property is easily seen if you do something which can also be done in higher dimensions. You can go to a dual model. So to say, you introduce link spins. You have spins which interact, and these are the spins which nearest neighbor interaction set sigma I plus 1. And this also, the product can only be +1 or -1, and call it mu I. It's a link spin, and then you can reformulate the model, and you see, instead of this product, you just have independent spins, and they have two states, plus G minus G, and which is the Heisenberg interaction, and you can calculate the partition function. But you can do this only if the magnetic field, the external magnetic field, is 0. But it could be done in more complicated cases to use such transformations of the original model. Now let me come to the other parts of the thesis, which are the more complicated cases he looked at, because he wanted to look at if in more complicated cases, he could adapt the model in such a way that he gets a magnetization. And one is that he allowed not only up and down, but also transverse positions in paragraph 6. He looked at the double chain, at the letter, and he looked at the linear change with not only next nearest interaction, but also next nearest neighbor next nearest neighbor interaction. So he took into account a second spin further away. So let me compare these three cases with what we know from now, work made now. But let us go first again to Schottky. So far, if you have the parallel and non-parallel position of the elementary magnets, you have circling electrons in the same or in the opposite direction. Now the transverse position would be the case for rotating electrons in this direction, in the plane, and then perpendicular to it. And you see, these configurations have different Coulomb energies, and also you see that here the Coulomb energy does not depend on the direction of the transverse spins, if it is rotating in this way or the other way around, and so on. And so he could also generalize and take transverse positions, more than one. But let us stick to the case where you have only the up position, the down position, and the transverse position. And he puts energies, again, Boltzmann weights, in an external field to these configurations. And for this transverse position, he had to have some external energy to keep it in some direction of the solid. So he has some external energy put here, and then he has the configurations up, down, transverse, and different Boltzmann weights for the different configurations, sigma 1, sigma 3, sigma 2, 3, and sigma 3, 1. So he has, in comparison with the first case, instead of 2 energy places, he has 3 energy places. So what he has to calculate is he has to calculate the partition function for the configurations with 3 places, up, down, transverse, the energy places, sigma 1, 2, 3. Then he has the Boltzmann weights for this configuration. And what I think what should compare with is there was 1922, Dom gave a topic to Potts for his thesis. It's the so-called Potts model. It's a model which also has more than one configuration for the internal elements, up, down, transverse, and or in some directions, let's say a clock model, or let's say a model where different hexagonal or every 30 angle in the solid, and so on. You can have an elementary magnet which can look at it. And so you have the case, if it is supposed that the energy of the interaction between 2 neighboring units is proportional to the scalar product of the vectors representing them, then when each unit is capable of 3 configurations, there are just 2 different energies of interaction. You can take a sigma 1 model where you have a spin -1, 0, and 1, and compare with it. And this is also important. I point to the this paper of the colleagues of Yuri, Ralph, and Sarkanch, and they had a model, looked at the Potts model, also a chain, a one-dimensional model, but with invisible states. And so, in my opinion, one could also look at the formulation of this model, which is in Ising thesis, to compare the results. Let me come further to the next place. I show you before that how he calculated the three-state model. Again, he summed up over all configurations independent of the condition and then expanded again. And so he got a partition function which has powers of 3, because he has a polynomial of 3, degree 3, of 3 eigenvalues of a corresponding matrix, so to say. And he compared some results with under assuming values for the Boltzmann weights, and made a plot in his thesis. And what you find for the values he used here, a curve which goes at low values of alpha along with the Langevin result. Now, modern theories also use three-state models in other fields. You have, for instance, a three-state model in the majority vote model. It's by Lima 2011 or Lichett 1985. So you have a voting of yes or no, or you follow a majority. So 3 states. You have the Sear model, which we have heard already about. It's the model of the coronavirus. You have models in market analysis. You can buy, you can sell, or you can hold something you buy on the market. And all these models can be formulated in respect to the three-state model, which Ising has suggested in his thesis. So I think I just shortly mention the other cases. It's the ladder configuration, and I think so I do not need to go into further details, because I think that he made an error there. He treated the ladder as the ladder where he has 2 chains as a chain by looking at the configuration of 4 spins. And they can be either in this configuration, he said, or in this, or in this, or in the configuration where all the elementary magnets are parallel. So I show this in the next slide. So these are all in they all are parallel. It has the energy 0. Here he has 2 energy places. Also here he has 2 energy places, or 2 energy places. And in this configuration, I think he forgot this configuration, he has 4 energy places. So one has to redone the calculation, in fact, to include this configuration. If I write down the model in the usual way with the configurations and the energy Boltzmann weights, you see this red one is a missing configuration. And what he gets is, he gets only a polynomial in the denominator, where he looks for the eigenvalues or for the zeros of degree 3. And in fact, for the chain, you get the degree 4. So one should redo with his method maybe his calculation and compare if he would have been right, if he could take into account these configurations. Now let me come to the other thing. He also looked at the next nearest neighbor interaction. So he looked at configurations up and down only, but also he took into account 3 spins. Then he has Boltzmann weights also with 2 energy places, depending if the third spin is or elementary magnet is down or up. And he calculated again in special cases the magnetization, he got in the same way as he did it, this factor which contains the external magnetic field, and so the magnetization he calculated is again 0. So in all his cases, he got 0 magnetization. Let me summarize. The Hamiltonian for the Ising model, looking like that, was presented by Pauli 1930 at the Soviet conference. Ising solved the two-state models exactly in 1924, and he proved that that mean field theory is false for the one-dimensional spin change. He extended the model to a three-state model, as I said. He also considered the latter and also next nearest neighbor chain, and in all cases he didn't get finite magnetization at any finite temperature. So if you want to know a little bit more about the Schottky model and its relation to the Ising model, I had the reference, but we also had have a common work between our groups with Tom Ising, myself, Ralph, Bersch, and Yuri about the life of Ising and the development of the Ising model. And I had last year the Ising lecture about that. Before I close, let me come to Ukraine back and to what I showed at the beginning, important places, important scientific landmarks. And there is an important scientific landmark in Ukraine, in Odessa, because there in Odessa, there was a conference, and Pauli, who invented in the same time when Ising solved his Ising model, the fourth quantum number characterizing the spin of the electron, and he was at a conference, and here is talking to Jakob Frenkel and Igor Tamm, one relative of the young physiker Tamm, who had some weeks ago a talk at the institute in Lviv. And another place is Kharkiv. It's the institute where Landau was, and also in Kharkiv you see here Niels Bohr, and I do not go through all the names. In the 30s there was a quite intensive activity between, let's say, Germany and Russia and Ukraine, and they had conferences, and they were in interactions. Some, like Piles, found his wife in Odessa, for instance. So it was a very vivid life between scientists of different countries. But war destroys these very important communications. Thank you for your attention.
Thank you very much. And please let us discuss, put your questions.
Hello, I have one question about this three-state Ising model. I wonder why there should be this coupling sigma 3,1 and sigma 3,2. Yes, here, why they should be different, considered?
Yeah, so well, they need not be different, but at that time you only have the idea that a magnetic moment comes about by a rotating electron. That was the status. And it should come about by electrostatic energy, electrostatic interaction. And so, similar to the Schottky model, I explain here by the figure that because of the configuration with a magnetic moment in that direction and a magnetic moment in that direction, you have different distances between the two electrons, and therefore different Coulomb energy of this configuration compared to this configuration or this configuration. But of course, this is a model which was replaced by Heisenberg's model, by the modern new quantum mechanics. But at that time, you only could assume that the configurations have a certain energy. The next point would be, you could consider not at the magnetic system, but you could consider an alloy, for instance, or a mixture with 3 different sorts of atoms. And then you can look at mixing, demixing, or phase transitions, and you can calculate the corresponding partition function for this model, again with the same theoretical ansatz, calculating the number of configurations and the Boltzmann weights. So therefore, this is a very general model to calculate very different physical situations, not only the ferromagnetic system.
Okay, thank you.
Thank you. Please, any questions, comments?
May I?
Please.
Hello? Yeah, thank you. Thank you very much for this talk, Reinhard. You know, I read your chapter to which you made the reference at the end, so I knew something about this talk, but every time I hear you, I learn something new. So for me, it was very impressive and very, very interesting. Thank you. And also for us, the common knowledge is that one-dimensional Ising model contains no transition, and people never look for the thesis, yeah? And it appears that in thesis there are so many, so far, not completely resolved questions that it is really astonishing and very, very interesting. I don't have a question. I just want to comment on the photo you showed at the very end of your talk. You know, it was Odessa 1930. And I want to share with you and with all other, you say Pauli and 1930 talking. Pauli 1930 talking to Frankel, and immediately I have two more reflections on this subject. The first one is about another physicist who is his name is Volodymyr Kucher. He did his studies in Lviv University before World War I, and he defended dissertation already then. And he was with Max Planck in Germany, and in 1930 he was in Lviv here, and Shevchenko Scientific Society in Lviv paid him for travel to this all-Soviet Union meeting of physicists in Odessa, because Lviv was in Poland and Odessa was in Soviet Union. And we know from his memoirs that he was going to Odessa by train, and he was sharing the compartment with Pauli, and he got acquainted, you know. So the world is really very, very, very small. And another reflection, of course, is about Frankel, because Frankel, again, between his many PhD students, was also the student who was named Abba Glauberman. And Abba Glauberman was born in 1917 in Odessa, in Warsaw. But already in 1918, his parents moved to Odessa. So in 1930, he was 12 years old. And then he did PhD with Frankel in Leningrad, now Petersburg. And then he went to Lviv after the war. And his student was Igor Yukhnovsky, who is the founder of the School of Statistical Physics. And that's why we have here these Ising lectures, because he taught us statistical physics. So that's just two reflections looking on this picture.
when I look at these historical things, I have the impression there is something going on, because there was so much connection between the different peoples. We have heard today that there are only 6 links between 2 people if you choose them randomly. It's in some way this is, but of course, if you are in a free country and if you can go over boundaries, then you have a large community of physicists which communicate in conferences and travel to each other and so on. So that's really what is very important for science.
Yeah.
But not only for science, of course. But it was in the 30s, it was possible. But in the Stalin time, then it was the borders were closed, and there was less communication between Russian countries and Western countries.
Yeah, if I'm not mistaken, the year 34, if I'm not mistaken, that's the year when Landau was imprisoned. And in fact, 1 year before he was in Kharkiv, and, well, 1 year before he was in Kharkiv, and he wrote these famous papers on phase transition theory, which there is Landau's theory.
In the internet, there's a description to these people, to this picture, what are the people are and their fate.
Yeah.
So some came to prison, some came to death, and so I didn't want to show this.
Thank you.
Thank you. Okay, if there are no questions, let us send.
Okay. Thank you.
And before I pass the word, let me congratulate all Ukrainians and all who support Ukraine. Today is Ukrainian National Day by a Ukrainian traditional shirt called Vyshyvanka.
Thank you.
Okay. Bye.
So now, thank you, Dmytro. Thank you, Ralph, for sharing today, and thanks to Reinhard and Joseph. And now we have the last item of our agenda, which is the closing.